Hello and welcome to our last video on Chapter 1. This is going to cover Section 1.7. The big idea in this section is reliability of measurement. And here we have a number as a measurement, 45.872, and it's telling us that the last digit is estimated. Whenever we measure something, the last digit will always be estimated. Sometimes we have to do that ourselves if we're using analog instruments, and sometimes the instrument will do it for us if we're using things that are digital. The more digits we have, it tells us the more certain that measurement is. So for example, if I asked you how much money is in your wallet right now, if you were very certain, you might say $23.42. If you weren't very certain, maybe you hadn't looked in it in a while, you might say $20. Now, each of those are about the same amount, but $20 only has one digit, it only has the 2, whereas $23.42 has 4 digits. So it shows you the different amounts of certainty. Now, the instruments are going to provide us with how much certainty there is, because some are meant to measure with more details and some with less. And so that's something we'll talk about as we do labs. Once we have these measurements, a lot of times we do calculations with them. And we want to keep the level of certainty consistent as we do our measurements. And so we have to talk about something called significant figures. And this is going to be a way to allow us to keep that certainty consistent. So there's 5 rules with significant figures, and we're going to practice these. We just have to go over the rules first. So rule number 1 says that all non-zero digits are significant. So anything that's not a 0, 1 through 9, these are always significant digits. So that means the rest of the rules are about zeros. Number 2 says interior zeros are significant. So a number between a 0 between 2 numbers, so 403. The 0 would be significant. Leading zeros are not significant. So if we have 0.03, those zeros are just there to show you the size. They're not significant digits. They don't tell you anything about the value of that number. Trailing zeros after a decimal are significant. So if we had 4.000, all of those zeros are significant because they're not telling you anything about the size of the number, but instead they're telling you about the certainty of that number. And the last one's the tricky one. Trailing zeros in front of a decimal are ambiguous. So this would be 3,000. So we're going to assume that they're not significant, and we can avoid it by writing that number in scientific notation. So if the number was 3,000, we can assume that only the 3 is significant and write it as 3 times 10 to the 3rd. Now, if we took that measurement and we knew that maybe that first 0 was significant, we could write it as 3.0 times 10 to the 3rd. Now that 0 is a trailing 0 after a decimal, and we've just made it significant. There's one more type of number. It's called an exact number. Exact numbers don't have any uncertainty. We know them with absolute certainty. And so when we're asked how many significant digits one of these numbers contains, the answer is always infinity. So there's 3 categories. Counting, so 10 chairs has an infinite number of sig figs. There's no uncertainty there. Definitions. So these usually come in the form of conversion factors for us. So 12 inches is equal to 1 foot. It's exactly 12 inches, exactly 1 foot. There's no uncertainty. And integers. So the example here is that if we take a diameter and divide it by 2, we get the radius. So this 2 has an infinite number of sig figs. This last one doesn't show up too much for us in chemistry, but every now and then. So let's practice this. Number 78 says how many significant figures, and this is how we generally abbreviate it, sig figs, are in each number. So 0.1111. Well, we have 4 non-zeros right here, And then we have a leading zero. So we know a leading zero is not significant. So this has 4 sig figs. Over here, we have 1, 2, 3, 4, 5 non-zeros. And then we have zeros that are after a decimal place. So those are also significant. So the 5 non-zeros, the 2 zeros, 7 sig figs. Down here we have 1 non-zero, and then we have 4 zeros. These 4 zeros are leading zeros. Leading zeros are never significant. So this number is only 1 significant figure. 30,800. The 3 and the 8 are significant. We have an interior 0, so these first 3 digits are definitely significant. And then we have trailing zeros. So these are those ones that can be a little bit tricky, but we're going to assume that they're not significant. So this number has 3 sig figs, these first 3, and we can write it a little bit better. So 3 sig figs, and instead of writing it like this, where there's some uncertainty in the certainty, we can write it as 3.08 times 10 to the 4th. This number is going to give us the same troubles. The 1, 8, and 7 are all significant. We have an interior 0, so we have 4 sig figs, and then we have these trailing zeros. So we have 4 sig figs, and we can write it in scientific notation to avoid any confusion. And then this last one, 24 cars. Now notice that all of our other measurements had units, seconds, meters, kilometers, but this one has counting, 24 cars. This is one that we would know with certainty. So this has an infinite number of sig figs because it's an exact number. Now, usually we're doing math with these numbers. So once we start doing math, we have to keep the level of certainty the same. So we have 2 rules. The first one is involving multiplication and division. And the rule says that the answer will have the same number of sig figs as the value with the least. So here's our math problem. And we count the sig figs in each of these values. So there's 4, 5, and 2. So our answer can only have 2 sig figs. It can only be as certain as the least amount. So this is the number your calculator gives you. Your calculator doesn't care about sig figs, and we're going to round it to just 2 sig figs. The rule with addition and subtraction has the same purpose, but we get there with a different way. So the rule with addition and subtraction says that the answer will have the same number of decimal places as the value with the least amount. So here's our 3 numbers. We have 3 decimal places, 2 decimal places, and 4. So because there's a 2 in there, our answer can only have 2 decimal places. Now this slide's about rounding. I'm sure you know how to round, but this is just reminders. So as we're doing our addition and subtraction and multiplication and division, we don't want to actually round until we get to the very end of the problem. So we are still following order of operations. So we do those parentheses first. Here's the number our calculator gives us. Now we have 3 decimal places and 2 decimal places, and we're following the decimal place rule because we're doing subtraction. So we only keep 2, but we're not done with the math. So we underline that second digit, and then we can continue with the math. So now we can do our multiplication. We know we have 3 significant figures, 4 significant figures, and because of this underline, we know this one only has 2 significant figures. So we're going to round this number to just 2 significant figures. When we're rounding, we always look at the number behind. So this is my last significant digit. I look at the number behind it. If it's between 0 and 4, we round it down. If it's between 5 and 9, we round it up. So this is the part that I'm sure you remember from other math classes. So we are going to practice rounding to 3 sig figs. So we have 59,845.82. If we're going to round this to 3 significant digits, we start on the far left, we start with the farthest left significant digit. So that's a 7. And we count over to how many we want. So 1, 2, 3. So that 8 is our 3rd significant digit. We look behind it, it's a 4, so we're going to round it down. So we get 79,800, but that does give us those bad zeros, so we can rewrite that as scientific notation. Over here, 2.9999995. So our third significant digit is that 9. We look behind it, it's another 9. Now 9s can be tricky because they make you round up a couple times. So this 9 makes that one round up, makes that one round up, makes that round up. So 2.99 rounds up to 3.00. Over here, there's our third significant digit. We look behind it, it's going to make us round up. 1.55 times 10 to the 7th. Now notice that this stays, nothing changed with that, because that's just there to tell us how big the number is. And the size of the number hasn't changed. And then over here. Now remember I said to underline the significant digit farthest to the left. These zeros aren't significant, so we're not counting those. We're going to underline the 3, because the 4 is the first significant digit, 5, 3, and 8 is behind it. So we're going to write it as 0.0000454. Now we could also put this one into scientific notation. It's definitely not necessary, but sometimes it's easier than making sure you've counted all those zeros. So we're also going to practice the math. So we're going to do it with multiplication, division, we're going to do it with addition, subtraction, and then we're going to put the two things together. So it says calculate the correct number of sig figs. So I know that you can put this all into your calculator at once, but I'm going to do it in pieces. So I do this part first. We get 6976.1, and we still have the times 0.08 at the end. We do that, we get this number. Now your calculator doesn't care about sig figs, so this is the number your calculator gives you. We have to go back and look at sig figs. We get 3 sig figs, 3 sig figs, 1 sig fig. So because of that, our answer is going to round to one significant figure. So that's our first significant figure. We look behind it. Our answer is going to round to 600, or it would be better to put that one in scientific notation because of those ambiguous zeros. Down here we have 5.01 times 10 to the 5th divided by 7.8 times 10 to the 2nd. When we divide those, we get 642.307. We look at sig figs, 3 versus 2. 2 is the smaller number, so we're going to 2. We underline our second significant figure. We look behind it, and this rounds to 640. Or again, we can put that scientific notation to get rid of that 0. So addition and subtraction is next. And when we're doing addition and subtraction, now we're going to look at decimal places. So the question says to calculate the correct number of sig figs. So we do our subtraction. That's what our calculator tells us. We have 1 decimal place. We have 3 decimal places. So our answer is going to round to 1 decimal place. So we underline where we're going to stop it. That's the first decimal place. That's where we're going to stop it. We look behind it. Because it's a 7, it will round up. And we get 0.7. Down here, we do the addition part first. We're just going to work left to right. And we get 539.3. We're still going to subtract the 48.523. So we get this. Again, we look at 0 decimal places, 1 and 3. We're going to round it so that it doesn't have any decimal places. So we underline where we're going to stop it. We look behind it, and it rounds up to 491. Now, when we start to put these together, meaning we are going to use both rules, because now we have multiplication and division and addition in this first problem. We're going to follow order of operations, and we're going to follow the correct rule for each calculation. So as we do order of operations, we're doing the parentheses first. We're doing our division. Now there is multiplication in here, but really that's representing the scientific notation. So when we do that division, we get 6.46, and we're still adding that 7.3. Now we don't want to round it yet, but we do want to know where that number should cut off. So we have 2 sig figs, 3 sig figs, so I'm going to underline this 4, because that's the second significant figure. And we're looking at significant figures because it was division. So now we're going to add. Again, that's what our calculator tells us. But we want to know where this number needs to cut off. And because we did addition, we're going to look at decimal places. 1 decimal place, 2 decimal places. So our answer, we're going to cut it off at that first decimal place. We look behind it. It's a 9, so it's going to round up. So our final answer is 13.8. So we're going to do the same thing down here. We have subtraction first. So we get 336.89. We're still going to divide it by that 5.3. But first we want to underline where this number will stop being certain. So we have 2 decimal places and 1 decimal place. So the 1 is smaller. So we underline that first decimal place. We do our division. We get 63.56. And now because it's division, we're going to look at significant figures. We have 4 significant figures. 1, 2, 3. The 8 is that last one. So there's 4. And 2. So we're going to stop it at 2. So there's our second significant figure. We look behind it. We're going to round up. So our final answer is 64. Now this is something we're going to do throughout the whole semester. So this is a really important topic to make sure that you grasp. Most of the time we won't be mixing math functions. It will usually just be multiplication and division together. But it's a good thing to know. So come back to this video and refresh yourself as you need to. There's a couple more topics in this section, and they're about error and precision and accuracy. So this one's really just about the definitions of the words precision and accuracy. And this is another one of those times where these words often get interchanged, even though they do have different meanings. So I'm going to start with accuracy. Accuracy tells us how close we are to our goal or to a target. So in our little pictures, our little silly pictures up here, this is an example of good accuracy. All of the little marks are right around our bullseye. And here is some poor accuracy. All the little marks are far away from our target. Precision is a measure of how close your values are to each other. So I like to think of it as how consistent you are. You can be consistently bad. So for example, here's my consistency. If we look on this one, all of the marks are really close together. All of the marks are really close together. So these are both precise. Down here, the marks are all spread out in both examples, so they are not precise. So here we are close together and close to the goal, so we have good accuracy and good precision. Down here, they're all spread out, so we have poor precision, and they're not close to the target, so we have poor accuracy. And then the last thing is 2 types of error, random error and systematic error. So we have 3 students, student A, B, and C, and we have their data from an experiment. So the graph has mass on the y-axis and the trial number on the x-axis. So they were weighing something. The blue line represents the true mass. So we can think of the blue line as what they should have gotten, their goal. The dotted red line in each graph represents the student's average. So we can use that to see how close they were to the goal. So student A says that they are inaccurate and imprecise due to random error. So their average is not close to the true value, so that makes them inaccurate. And their actual data points are kind of all over the place. Some are too big, some are too small, so that makes them imprecise. Student B has an average value that's lower than the true value, so that makes them inaccurate. They weren't close to their goal. But all of their values are very consistent. They're all very close together. So student B is precise, but inaccurate. And so this is a systematic error. So this is something that they had an error in their technique or in the instrument, but it was consistent. So everything was either slightly too high or slightly too low, but there was still consistency. And then student C, our last student, their average, the red line, is right next to that blue line, so that tells us that they were accurate. And each one of their trials is very similar to the previous one. They're all very close together, so that tells us that they were consistent. So student C does not have any error. So random error is when we don't have precision or accuracy. Systematic error is when we still have precision, but we're not very accurate. And then when we have no error or very little error, we have accuracy and precision. All right, that's it for this video. Thank you.